I like to jump from solving systems of two equations into solving systems of three equations before applying them to the word problems. So here we have a system of three equations with three unknowns. Solve 2x minus y plus 3z equals to 1, x plus 3y minus 4z equals to 5, and negative 4x plus 2y minus z equals to 13. Alright, well, it's much easier to get lost in these larger problems, and you really need to be well organized in order to avoid a lot of the common errors. So unfortunately, with my small board, I can't show you the entire problem on one board. Not likely to. So I will have to do some erasing and rearranging. However, I want to give you some ideas of how you might try to stay organized with this. And one thing I like to do when I show this to classes is to label my equations. So the first equation I'm going to call circle 1. So rather than write 1, which I don't want to confuse that with a number, I put a circle around it. Here's equation 2 and equation 3. Now the technique for solving these is really quite similar to what you did in the last section. We choose a letter to eliminate. And I'm looking up there, and I think they're all good choices, but I would probably pick on y. Because if I multiply this equation by 3, then it will cancel with the 3y. And if I multiply this equation by 2, it will cancel with this equation. So my initial decision is which letter do I want to eliminate by making these equation adjustments. And then once we eliminate, in this case, the y variable, what we're going to be left with, as you'll see, are two equations with two variables, x and z. And then the problem will look like something you did in the last section. So we'll get started here. And I'm going to multiply 2 times, I was going to start with 3, wasn't I? I'm going to eliminate this 3y with that term. So I'm going to multiply by 3 times equation 1, and 3 times this becomes 6x minus 3y plus 9z equals to 3. Now be careful, I didn't write parentheses around the equation and multiply by 3, which would have been a fine thing to do. But be careful, because some students occasionally forget to multiply the right-hand number. That also has to be adjusted. Alright, to this I'm going to add equation 2. And so this is x plus 3y minus 4z equals to 5. And now if we add these equations, you'll see that the y term is eliminated because these terms cancel. So I'm left with 7x plus 5z equals to 8. Alright, so there's our first smaller equation. Now let's go ahead and by the way, that elimination involved the first and second equations. Now to proceed, I'm going to, and I think it'll become apparent to why I'm doing this, to proceed I've got to eliminate y one more time. And in so doing I have to involve the third equation because we haven't used it yet. So to eliminate 2y, I'm going to multiply the top equation, this time times 2. So 2 times equation 1 gives me 4x minus 2y plus 6z equals to 2. And then I add the third equation, and this is negative 4x plus 2y minus z equals to 13. And a surprise, I didn't know this was going to happen. We have a little bonus here. Not only did the y term cancels, but also this time the x term also cancel. So I'm left with zeros here. 6z minus z is 5z, and 5z equals to 15 by adding those two numbers. So I think most of the time you will get, if you were to eliminate y, then you would see two different equations with x and z. And then we've got to go from there and solve that smaller system of equations. And so you see the idea is we start with a 3 by 3 system, and by eliminating one variable, we shrink it to 2 by 2, and then we eliminate one of those variables and solve for one of the letters. And then as it turns out, as you'll see, we'll start going back and solving for the rest of the letters. All right, but here I got a little lucky, and in fact, it's even better than I thought. First of all, 5z equals to 15, then z is equal to 3. So let me write that up here. And that was by dividing that equation. And then I noticed that if 5z is equal to 15, then I can do a substitution right there. Now normally you would take the 3, plug it into there, but I already know what 5z is. 5z is 15. So this equation becomes 7x plus 15 equals to 8. And now if we subtract 15 from both sides and proceed to solve for x, 8 minus 15 is negative 7, divided by 7, x is negative 1. And then we still need to get y. So I know what x is, I know what z is, and I will have to do some erasing now. So how am I going to get y? I'll use the first equation. And so the first equation then is 2 times x, and x is negative 1, minus y, plus 3 times z, and z is 3, equals to 1. So we have negative 2 minus y plus 9 equals 1. And these terms combine. Negative 2 plus 9 is 7. Sorry there. That's negative y plus 7 equals to 1. And now subtract 7 from both sides. Minus y is equal to negative 6. And if negative y is negative 6, then positive y is positive 6. All right, well, we have answers. We haven't checked the equation yet to see if we got the right answers to verify it. But that sort of, in a nutshell, is the process of solving larger systems by elimination methods. So let's go ahead and check that. By the way, when we solve for two equations, we saw that it's common to write the answer as a coordinate point, a coordinate pair, like an xy point on a graph. In the context of these problems, it would be quite okay to write the answer as an ordered triple. And so x comes first, followed by y, and then z. So here is the answer to the problem written as an ordered triple. I think if you don't do it this way, you should take, the way I've written, I've got these scattered over the board. I think it would be better to rewrite them at the bottom of your problem. All right, but this is a fine way of writing your answer, and that represents a point in space, three-dimensional space. So I'll show that a little bit later, what I mean by that. All right, I'm going to check the answers here, and so